The video introduces the exploration of the origins of life. Scientific explanations for the origins of life will be examined. Folklore perspectives on the origins of life will also be presented. The video contrasts scientific and folklore accounts of life's beginnings. The video introduces the exploration of the origins of life. Scientific explanations for the origins of life will be examined. Folklore perspectives on the origins of life will also be presented. The video contrasts scientific and folklore accounts of life's beginnings. The origin of life is a fundamental question explored through scientific and mythological perspectives. Scientific explanations seek to understand the natural processes that led to the emergence of life. Mythological explanations often attribute the creation of life to divine beings or supernatural events. Both scientific and mythological accounts offer frameworks for understanding our existence. The question of life's origin continues to drive scientific inquiry and philosophical debate. Exploring the origins of life involves examining diverse fields, from biology and chemistry to history and philosophy. Creation myths across cultures reflect humanity's inherent desire to comprehend the origin of life. These myths commonly attribute the creation of life to divine beings or supernatural forces. Understanding these myths provides insight into the cultural values and worldviews of ancient civilizations. Despite their differences, creation myths share the underlying theme of seeking explanations for existence. Abiogenesis is the scientific concept describing how life arises from non-living matter. Abiogenesis is understood as a complex series of events, not a singular occurrence. The process involves a gradual progression from simple molecules to complex biological structures. Environmental conditions play a crucial role in abiogenesis. Abiogenesis is a fundamental concept in understanding the origins of life on Earth. Early Earth was characterized by intense volcanic activity and frequent eruptions. The surface of early Earth was constantly bombarded by meteorites and asteroids. Frequent lightning storms were a common occurrence in early Earth's atmosphere. These harsh conditions made early Earth a challenging environment for the emergence of life. The early atmosphere was significantly different from the atmosphere of modern Earth. The simulation illustrates the extreme conditions that shaped the geological and chemical evolution of early Earth. Early Earth's atmosphere was composed of a toxic mixture of methane, ammonia, and water vapor. The early atmosphere lacked free oxygen, making it uninhabitable for modern aerobic life forms. Volcanic activity contributed significantly to the release of gases into the early atmosphere. Water vapor in the early atmosphere played a crucial role in the formation of primordial oceans. The absence of an ozone layer allowed intense ultraviolet radiation to reach the Earth's surface. The primordial soup theory posits that life originated from simple chemical compounds in Earth's early oceans. Early Earth's environment provided the energy needed to transform these compounds into more complex organic molecules. These organic molecules accumulated in the oceans, creating a soup rich in the building blocks of life. This primordial soup served as a global chemistry experiment, fostering the conditions for the emergence of the first life forms. Lightning provides a significant energy source for molecular bonding in primordial environments. Volcanic activity contributes thermal energy that facilitates the formation of complex organic molecules. Solar ultraviolet, UV, radiation serves as another energy source for driving chemical reactions in the primordial soup. These energy sources collectively drive the bonding of simple molecules into more complex organic molecules. Amino acids are the fundamental building blocks of proteins. The formation of amino acids is a crucial step in the development of life from non-living matter. Amino acids link together through peptide bonds to form polypeptide chains. These polypeptide chains then fold into complex three-dimensional protein structures. The Miller-Urey experiment, conducted in 1952, aimed to recreate early Earth conditions in a controlled laboratory environment. This experiment sought to understand the chemical origins of life by simulating the primordial atmosphere. The setup included a closed system containing gases believed to be present in early Earth's atmosphere, along with liquid water. Electrical sparks were introduced to simulate lightning, a common energy source on early Earth. The Miller-Urey experiment simulated early Earth atmospheric conditions to test the possibility of abiogenesis. The experiment used gases thought to be present in Earth's early atmosphere. Water was included in the system to simulate early Earth's oceans. Electrical sparks simulated lightning as an energy source for chemical reactions. The experiment aimed to determine if organic molecules could form from inorganic substances under early Earth conditions. The Miller-Urey experiment simulates early Earth conditions to explore the origins of life. Electric sparks mimic lightning, providing energy to drive chemical reactions within the gas mixture. The energy from the electric sparks facilitates the formation of organic molecules from inorganic gases. This simulation demonstrates a possible mechanism for the abiotic synthesis of organic compounds on early Earth. The Miller-Urey experiment successfully produced amino acids, the building blocks of life. This experiment provides evidence that organic molecules can form spontaneously from inorganic substances. The creation of amino acids suggests a possible pathway for the origin of life on early Earth. The experiment supports the hypothesis that the conditions on early Earth were conducive to the formation of complex organic molecules. The Miller-Urey results demonstrate a potential mechanism for abiogenesis, the process by which life arises from non-living matter. Amino acids are fundamental building blocks, but they are not life itself. Life requires the organization of amino acids into complex structures. The arrangement and sequence of amino acids determine the function of proteins. Organized structures, such as proteins, are essential for biological processes and cellular functions. Self-replicating molecules, particularly RNA, represent a crucial step in the origin of life. RNA's capacity for self-replication is fundamental to its role in early biological systems. The formation of RNA molecules marks a significant advancement in the complexity of prebiotic chemistry. Self-replication allows RNA to propagate and evolve, driving the development of more complex biological functions. The emergence of self-replicating RNA provides a plausible mechanism for the transition from non-living matter to living systems. The RNA world hypothesis proposes that RNA, not DNA, was the primary form of genetic material in early life. RNA's ability to both store information and catalyze reactions supports its role as a precursor to DNA and proteins. Unlike DNA, RNA's simpler structure and catalytic properties made it suitable for early self-replicating systems. The RNA world hypothesis suggests a potential pathway for the evolution of life from simple chemical compounds to complex biological systems. RNA's capacity to transmit genetic information positions it as a potential precursor to DNA in the evolution of life. The information-carrying ability of RNA is a key factor supporting its role as the first molecule of life. RNA's genetic information capacity suggests its potential as a foundational element in the origin of life. The ability of RNA to carry genetic information is crucial to understanding its potential as the first self-replicating molecule. RNA's role as a genetic information carrier is central to hypotheses about the early development of biological systems. RNA possesses catalytic properties, enabling it to facilitate chemical reactions. The catalytic activity of RNA is crucial for early life processes. RNA catalysts, also known as ribozymes, accelerate reaction rates by lowering activation energy. Ribozymes exhibit specificity, interacting selectively with certain substrates. RNA catalysis involves mechanisms such as acid-base catalysis and metal-ion catalysis. The discovery of RNA's catalytic abilities revolutionized the understanding of molecular biology and the origins of life. RNA molecules are theorized to have evolved into more stable and complex forms over time. This evolution of RNA eventually led to the emergence of DNA-based life. RNA's inherent instability drove the selection for more robust genetic storage mechanisms. The transition from RNA to DNA provided increased genetic information storage capacity. DNA's double-stranded structure offer superior protection against degradation compared to single-stranded RNA. The development of DNA marked a significant advancement in the evolution of life. Life likely originated through a gradual process of chemical evolution. Chemical evolution begins with simple atoms combining to form basic molecules. These basic molecules then assemble into more complex organic compounds. Complex organic compounds further evolve into self-replicating molecules. Self-replicating molecules are a crucial step in the origin of life. This gradual chemical evolution ultimately leads to the emergence of the first life forms. The convergence of highly improbable events can be considered a remarkable occurrence. Such coincidences defy typical expectations of randomness and statistical likelihood. The perceived miraculous nature arises from the extremely low probability of the combined events. These unlikely combinations often lead to a sense of wonder and disbelief. Despite their improbability, these events are still governed by the laws of probability. The origin of life is a subject of ongoing debate. One perspective suggests life arose from a series of random cosmic events. Another perspective posits that life is the result of intentional divine design. Both perspectives offer explanations for the complexity and diversity of life. The question of cosmic accident versus divine design remains an open philosophical inquiry. Humans possess the unique ability to contemplate the origin of life. This capacity for introspection distinguishes human consciousness. The act of questioning is fundamental to understanding existence. Awareness allows for the exploration of complex philosophical concepts. Contemplation fosters a deeper connection to the universe and our place within it. Viewers are encouraged to share their thoughts and opinions. The comments section provides a platform for audience engagement. Constructive dialogue and diverse perspectives are valued. Feedback from the audience can foster community and improve content. Comments contribute to a richer understanding of the subject matter. Viewers are encouraged to like the video, to show their appreciation and support the content creator. Subscribing to the channel ensures viewers receive notifications about new uploads and content. Clicking the notification bell alerts viewers when new videos are released. These actions help grow the channel and allow the creator to produce more content.